Good afternoon, everybody. So I will speak about sand transport, ripples, and dunes. So first, a few words about the phenomenology of these things, and then sand transport, bed shear stress, and ripples, and I will finish with the case of isolated Barcan dunes. So a few pictures about these ripples and dunes. So what we call ripples are centimetric bed forms, which form on any erodible bed of particles, which is sheared by a fluid flow, which may be air or water. But here I will mainly speak about water or liquids, bed forms under liquids. These ripples are those that you see on beaches, except that on beaches the ripples we see are formed by the oscillating motion of the water induced by the waves, the surface waves. But the mechanism of the instability is the same under oscillating flows or under steady flows. So, for example, you have here a picture of ripples in an open channel flow with sand, with typically the sand diameter is about 100 microns. Here you have ripples with much smaller particle diameter, which means that even if the flow is turbulent, the grains are embedded in the viscous sublayers or in the laminar flow, so that which shows that turbulence is not an essential feature for the growth of ripples. You can see also that the pattern may be complicated and that it evolves with time. Here it's nearly the same shear stress, but it's after 6 hours, 20 hours, 24 hours. So the patterns may evolve slowly in time. And finally, we can observe also ripples under viscous flow, here under positive flow in pipes. Here you have another example of such ripples which have been taken in our lab and at IMFT in Toulouse. Our institute is built on an island, and when the river floods, we have water in the lab, and here is the shape of the flood wave, which is over several days. And here, when the water goes out, we end with much mud in the lab, and in particular with such ripples. So this is ripples in the lab, but not very well controlled. So if we want to have better control of what happens, I have a little problems with file formats. So here it's ripples appear in a channel which is seen from above. So the total width of the channel is 12 centimeters, and the thickness of the water is 6 centimeters. So you clearly see at the beginning we have a flat bed, and ripples grow, and with a well-defined wavelength. Sorry?
The video was in real time?
Yeah, real time. Yes, it's real time. It's real time. So this is what we have seen. And now there are some much larger bed forms, which we call dunes, which are typically with wavelength about 10 or several tens of meters and height about 1 meter. And these dunes form in particular at the bottom of rivers. Here you have the Rhine River. It's the Rhine River which flows from right to left. And what we see, these gray and white bands, corresponds to bed forms, which are dunes, which are at the bottom of the river, and with typical dune height about 1 meter, dune length 22 meters, and flow velocity about here 2 meters too. And the water depth is 10 meters. And the grain size is much larger than previously. Here it's about 3 millimeters. So first question, is it the same mechanism which makes grow small ripples or large dunes? And this question is not completely well answered, because there are in fact 2 mechanisms. Either the large dunes are formed by the coalescence of small ones merged together, or it may be the result of a specific instability, long wave instability, and these 2 mechanisms are possible. In general, these long waves These dunes are formed rather by the coalescence, because the time to reach such dunes by the coalescence process is lower than that which would arise with the growth of a long wave instability. And the third bed form, typical bed form, is what we call banks, which are completely different bed forms. Here you have such banks. Such banks in the channel between France and England. So the water is shallow, about a few tenths of meters, and these banks. You have here a detailed picture of a bank. You see whose length is about kilometers and height about 10 meters. And these banks are aligned with the current. Here we have the tide currents which go up and down, and these banks form these large bed forms form which are aligned with the main current. So three kinds of bed form. No, it goes up and down. There are upwards velocity to the north and then to the south, between the Atlantic Sea and the North and the sea above.
Because temperature is also working.
No. It's tide. It's a uniform. It's a uniform velocity during 12 hours, 6 hours, and another velocity during the six following hours. So now we have to, underwater. Yes, of course, at the bottom, at the sandy bottom. So now we have to turn to sand transport and the mechanisms which are at work in such problems. So the transport of particles, which may be spherical or also have some more complicated shape. This problem is controlled by many parameters. In particular, the particle diameter and density, the fluid, water or some other fluid, viscosity and density, the shear stress imposed by the fluid flow on the bed, gravity, which is embedded in the falling velocity, US, and then the flow depth or the boundary layer thickness, delta. So with these dimensional parameters, we can form 4 dimensionless parameters, and among these 4, 2 in fact are important, which are what we call the Shields number, theta, which is the shear stress normalized by the apparent weight of the particles. So this is, if you multiply by d squared, you have a force, which is the scale of the force acting on a particle divided by the apparent weight of the particle. This is the Shields number. And the characteristic of this kind of motion is that we have a threshold to induce motion because of the disorder of the bed surface. And the other important parameter is the sedimentation Reynolds number, which is built with the sedimentation velocity, or what we call the particle Reynolds number, which is built with a typical fluid velocity at the bed level, which is here the friction velocity defined here. So these 3 parameters are not independent, so there are 2 independent parameters. Now we need an equation for bed transport, and we developed with John here present a little model for such bed transport, which would account for relaxation effects, I will explain, and perhaps small particle Reynolds number effects. So if we make a mass conservation of the moving particles in a small slice here, and call n the number of particles, of moving particles per unit horizontal area, the mass conservation implies that the variation rate of this number n equals an erosion rate from the fixed bed, the particles which are fixed and which are entrained in the moving layer, minus a deposition rate, which is the inverse, deposition because of gravity, minus the net flux which crosses this slice, which is the divergence of the particle of the volume flux. And the volume flux itself is the product of the number n times the characteristic, the mean velocity of the particles. And here we have three quantities that we need to be modeled: the erosion rate, the deposition rate, and the particle velocity. So for the velocity, we can simply write that the velocity, the particle velocity, is proportional to the friction velocity, which is again the flow velocity at the scale of the grains. And we have also to introduce some thresholds because, as I said previously, because of the disorder of the bed. Then for modeling the deposition rate, we can make the remark that this rate must be proportional to the number of moving particles divided by some deposition time, and this deposition time must involve the characteristic settling velocity US or U reference divided by D with some coefficients here Cu and here Cd to be determined by some experiments. And the third term is the erosion rate, which is controlled by the fluid flow, and we can write this erosion rate as 1 over an erosion time, and this erosion time must be related to some deformation rate of the flow. And for viscous flow, it involves the shear rate, gamma dot, and for turbulent flow, it would involve the ratio of the friction velocity and the particle diameter. So, and again, we have a coefficient. So we need to determine the three coefficients here, and we have no other choice that make experiments. Yes?
Question regarding the first equation. How are you getting, why is it square root of theta?
Because theta is defined by the shear stress, which is the fluid density multiplied by the velocity u square, by the square of the friction velocity. So theta involves the square of the friction velocity. So the square root of theta is proportional to the friction velocity.
So theta is not the shield number.
Yes, it's the Schill's number. It is dimensionless. It is dimensionless. It is the ratio of a shear stress divided by the product rho dg. So it's a dimensionless shear stress, and the square root of theta is a dimensionless fluid velocity at the particle scale.
And in UT, capital UT.
And UT, we observe that when the Schill's number exceeds the threshold, the particles begin to move, but their initial velocity, they begin to move from zero. So we have to introduce a threshold for the particle velocity too. And so the above equation for mass conservation may be simplified to this very compact equation, which is an equation for Q, which is the flux. Here it's little q, before it was capital Q, but it's the same, which is the product of N by U, the particle velocity. And this equation is a simple relaxation equation, which means that in a uniform situation where there is no gradient, the actual flux is equal to some saturated flux, which is a function only of the bed friction, tau. And for an homogeneous situations, here we have a gradient, and so the flux evolves, the flux Q evolves according to a very simple first order relaxation equation, which involves only one parameter, which is the saturation length. And with the previous modeling, this saturation length is proportional to this quantity, which is the ratio of the friction velocity and the settling velocity multiplied by the particle diameter. And in fact, this is a deposition length. It is the length which is needed for a moving particle to fall onto the fixed bed under the shear stress tau and the friction velocity u star. And what this equation, what is new in this equation is this unsteady, or not unsteady, inhomogeneous term, because previously people was taking a particle flux which was always the equilibrium flux under the shear stress to the bed shear stress. So how do we determine the coefficients? To do that, we have done experiments under viscous flow, under viscous fluid, in a quiet flow of silicon oil. And so you see, so the flow is from right to left, and you see here the particles moving on the bed. And you see that this is nearly a monolayer of particles which are doing some small jumps or which are rolling on each other, and with some well-defined mean velocity. And so this is for acrylic grains with this diameter. And here the particle Reynolds number is smaller than 1.
Square flow is the inner wall that is moving, or the outer wall? So which part are we?
Yes, sure. This is in an annular channel, and the upper plate is rotating so that to entrain the fluid. So it's a quad flow with the upper plate moving. Yes, the upper plate is moving to the left, and in order to have some periodic conditions and avoid entry and exit effect, we bent the channel. But here the rotation does not intervene in the problem. So this is what we see, and from above we can take pictures of the motions with cameras and determine from this the variation of the particle velocity with time. And the first thing that we see is that it's highly intermittent. It's a highly intermittent motion. It's not a constant velocity motion, highly intermittent. And if we, from this, so here you have the velocity of one particle during time, then this particle exit the frame of visualization, so we take another particle, etc. And then we can plot the PDF, the particle density function, of these velocities, and find that this PDF is exponential, which means that there are many particles with small velocities and few particles with high velocity. And here the mean is a fraction of gamma d. Gamma d is the product of the shear rate times the particle diameter. It's the fluid velocity at a distance of one diameter above an horizontal ground. Okay, so it's a fluid velocity at the scale of the particle, and the mean velocity is 1/10 of this characteristic velocity. And we can also we observe that the particles make some jumps, and we can determine from these measurements some flight duration, and we find a distribution of flight durations. And here the flight duration scales with the settling time, which is d over the settling velocity vs. And you see that here the mean flight duration is about 10-15 times this characteristic. And we have also tried to see what happens inside the moving layer, because when we see from above, we have only the motion of the surface particles. And there are some particles below which are moving slowly, much slower than at the surface, but they are moving. And it's interesting to know how these particles move below the surface. To do that, we have matched the index, the optical indexes of the fluid and the particles, so that the channel is fully transparent. And we dyed a few particles and put a laser sheet, and we have this kind of picture. So here it's seen from the side, not from above, but from the side. So below we have the fixed bed, then a moving layer, and then the clear fluid. Fast particles at the top of the moving layer, and small particles at the bottom or near the fixed bed. So I do it again. If you follow, for example, this particle here, it doesn't move. This one does not move. but some others move slowly. So, and from these measurements, we can obtain the the velocity profile inside the moving layer, and we find that it's a parabolic velocity profile with a curvature like this. And we also measured the fluid velocity in between the particles using PIV, that is for particles much smaller than the grain diameters. And so we have velocity profiles of the particles and of the fluid. And we see, I have not here the picture, but we see that as we can imagine, the particles move slowly or more move with less velocity, less speed than the fluid particle. And we also can assess the hypothesis that we can write the total shear stress as the sum of a fluid shear stress in an effective fluid plus a particle shear between the particles, shear stress between the particles. And the effective fluids means that we have here a viscosity which is not the molecular viscosity, but which is a sort of kind of turbulent viscosity, which accounts for the fluctuations, for the velocity fluctuations of the fluid due to the motion of the particles. And here, this shear stress obeys a simple Coulomb law. That is, it is the product of the friction coefficient multiplied by the hydrostatic pressure.
Moving layer is hardly 2 to 3 particle diameter. The moving layer.
Yes.
2 to 3 particles.
Yes, approximately. It's 2 to 3. And when we increase the shear stress, the thickness increases too.
So when you say parabolic profile for a 3-layer, it's just that.
Yes, it's a parabolic profile for a thickness of about 2, 3, 4 particle diameter. But as we have many particles, we can obtain converged profile. So now we have all we need for describing the particle motion. So we turn to the instability of a flatbed and ripples. So first we need to understand the fluid motion above a fixed wavy bed, a fixed wavy surface, and there have been not many measurements, in particular those of Anrati, who showed that for small wave slope, the shear stress, which was measured by an electrochemical method, the shear stress is sinusoidal, and it's with a phase which drives, whose phase is ahead that of the bottom. There is a phase difference between the shear stress and the elevation of the bed. And if for larger wave slopes, the amplitude of the shear stress is larger, of course, and we see that the wave is no longer sinusoidal, which means that we have nonlinear effects and the growth of harmonics. And so here we have other measurements and results of large eddy simulation made by these people. For here in red, it's the measurements for this large wave slope, and in blue, the blue lines corresponds to simulations with wave slopes varying from 0.04 for the dotted line, which is nearly sinusoidal, up to 0.6. And here you see that for a large wave slope, we have something which is very far from sinusoidal. And then we tried, so people tried to model this response, and mixing length models have been used and to determine the bed shear stress, that is the component A, which is in phase with the displacement, the elevation of the bed, of the wall, and B, which is in quadrature. And here you have the plot of A versus the wave number normalized with some equivalent roughness, bed roughness, and here you have the component B. So this is a complicated picture. I will not discuss all of it. Just say that for large wave numbers, for small wavelengths, the penetration depth of the disturbance induced by the bed is remains inside the laminar region of a turbulent flow, and for long wavelengths, for large wavelengths, the penetration depth, which is 1 over, which is the inverse of the wave number, this penetration depth is enters the turbulent region, and there is a transition region, and unfortunately, the ripples we observe are all in this complicated transition region. And the green points corresponds to the measurements of ANRATI, which are also in this region. And the classical modeling do not account for this rapid variation with this peak here that ANRATI observed. And ANRATI understood that it could be accounted for by the fact that the Van Drist length, which is involved in the definition of the logarithmic velocity of the velocity profile, of the flow velocity profile, is modulated. This length is modulated by pressure effects as the flow is successively accelerated on positive slopes and decelerated over negative slopes. So he introduced a phenomenological model for describing first order model for describing this effect, and with this phenomenological law, he obtained a good agreement between measurements and prediction. So now we have the flow, we have the particle motion. So we combine the two and form to form ripples. So on the side of the fluid, the shear stress, as we see, is in advance with the bed elevation. So there is we can define some fluid inertial length here between the maximum of the elevation and the maximum of the shear stress. If the particle flux is the saturated flux, then the granular flux is in phase with the shear stress. So that, since there is a phase advance of the granular flux, particles accumulate on the crests, and so that we have an instability. The amplitude of the ripple grows. On the other side, if we take into account some relaxation effect, the maximum of the particle flux is no longer corresponds with the maximum of shear stress, but we have some deposition length, which is exactly this saturation length. And if this deposition length is larger than the fluid inertial length, then the granular flux lags, and we have stability, because the particles are leaving the crests and fill the troughs, so that the instability disappears, the ripple disappears. So we have this simple criteria for the instability with the sum of these two lengths, and with this mechanism, with this deposition mechanism, we have a stabilization of short waves and a much better prediction of the ripple length than before. So with this, we have a good. We have to adjust the saturation length, because it's very difficult to measure the saturation length. It has been measured in air, but in air the saturation length is much longer. It's about 1 meter. Underwater, it's much shorter. It's about 1 centimeter, and it's difficult to measure. But we can adjust it with reasonable values, and then we obtain a good agreement of the measured wavelengths here, measured by many people, versus the particle diameter, which is this parameter d over the roughness is the main parameter. So and the line here, the black line, corresponds to the model of ANRATI, and plus the saturation phenomena, the saturation phenomena of the particle flux. So we can consider that we have a good description of these ripples. And another phenomena interesting is that these ripples have not exactly the same wavelength and the same velocity, so that they merge together, and as I said before, they form progressively larger and larger wavelengths, and this phenomena is illustrated here. Here you have space, and here time, and you see that here we have small wavelength and the coalescence process, which leads to large wavelength. And here you have the mean wavelength plotted versus time, and we see that over long times, about 1 hour, this wavelength increases and perhaps stabilizes over a constant wavelength. This is not sure. It could be a slow logarithmic growth, which with growth rate increasing smaller and smaller. And finally, we end, or we nearly end, with wavelengths here, which are much larger than the initial ripple length. Bark and dunes. How time does I have? 5 minutes. 5 minutes for bark and dunes. So bark and dunes are very interesting objects which develop at very different scales. They are very well known in deserts, and these dunes are the form of a crescent with the horns directed downstream of the airflow. And here it's they grow on poorly erodible grounds or non-erodible grounds. So there are sand heaps which travels under a constant wind direction. Here we see three such dunes. The typical size is 100 meters and the typical height about 10 meters. And these structures can be seen also on ice and in channels at small scale. Here, this is underwater. It's a picture we have obtained in Toulouse. And here the size is about a few centimeters. And we can observe also these dunes in pipes, in circular pipes. And to form these dunes in laboratory, we start from, this is view from above, we start from a conical shape. So we have a syringe here to inject a small volume of particles. So we form a heap, a conical heap. And as we put the flow on, here from left to right, the sand heap tends to travel downstream, and it quickly evolves with this characteristic shape. And so now I show you the dune motion, such a bark and dune. So here we have about 5 or 6 centimeters. And you see the particles at the bed surface, which are moving downstream, and they reach the avalanche phase here, but they do not leave the particle. They stay, so you have seen, they stay on the particle, on the dune. So they have a very constant shape, and this dune it's not exactly self-similar, because here we have an offset, always a little offset. This could be a subject of discussions, but I have no time. So we measured the velocity of the dune, and we obtained a good general correlations, which is this one, which is the velocity of the dune is proportional, in particular, to the shear stress to the power 2.5. But we have no explanation for this empirical law, and so I will. So to understand this law, we made a lot of measurements of flow measurements above the dune or in a turbulent flow, and so I have no time to explain these interesting things. And we measured also we verified that the mixing length model is a good model for the flow over dunes. And we measured the mixing length. Y over delta A. Y is the depth, is the distance, and delta I, this is the profile. This is the length L of the mixing length, which is obtained by dividing the turbulent shear stress, which have been measured, and the gradient of the mean velocity, which has been measured too. So from these two measurements, we can deduce the length L and check the Brandt mixing length model, and check that it gives good results with here a viscous layer where there are no turbulent stresses, and delta Y is the distance from the bed which separates a region, an outer region, where stresses are unimportant, and an inner layer where these stresses are important. So, but I have not, I cannot. It's a question of the interaction between different. So, here we have several dunes propagating in the channel, and as I said previously, small dunes propagate faster than large dunes. So there are interactions between them, and you can see here a complicated interactions between three dunes. So, and at the end, we recover. At the end of the interactions, we recover the same shape. So this is a very robust shape. We have here these two, and then another. I think that so these two dunes propagate with a characteristic relative position, which is this one, and I just weighed a smaller one. Yeah, here you have a smaller one, which arrives and which collide the two others. And
so you're basically having a channel in which you're dropping heaps of different heights.
yes,
And then you're blowing air, and then the heap slowly deforms in the shape of this dune.
yes,
And then that dune moves to the constants.
exactly.
And so, do you have any explanation why do you get this sort of, this uniform shape, especially
The curvature of the
the backside
of the avalanche face, the curvature.
the backside?
No, I have no. We have no modeling of this shape. Yes, it's an interesting question. What fixes this shape, the curvatures, etc. But I don't. We have no.
Recirculating it.
Yes.
Trailing it in downstream. Like that.
Yes, the stability of the dune is due to these trailing, to these longitudinal eddies which form downstream of the avalanche shape. This streaming, these two vortices, upstream, downstream, are rotating such that they drag the particles to the center, and then the dune sweeps them, and so that they can stay in the dune. But this does not explain the shape of the with positive slope. The shape does not depend on the initial shape. The final shape, the dune shape, does not depend on the initial shape. You can put whatever shape, heap like this, it will always evolve towards this shape.
We have a colleague of ours who is currently doing, but she works on salting out effect. So you have a granular gas, a gas with granular.
This is on the liquid. What I was showing here, all our experiments are under water. Water. But in fact, we observe the same in air, except that in air, these dunes are much larger. And the reason is in the density ratio. Density ratio between sun and air is about 1,000 that between sun and water. And we recover the same scale difference of 1,000 between small dunes under water and large dunes under air.
So in her experiment, she has a gas which carries granular.
It's a liquid. In our experiments, it's liquid.
Yeah, but in her experiment, it's like a gas. And then the particles settle at a certain distance, and then they start salting. So she calls it as salting out effect. And then they start forming dunes.
Yes.
And of course,
On non-erodible grounds.
So a dune is formed out of a particle-laden gas.
Yes. John.
The density ratios are so different that
So if I remember correctly, at one stage, the things might have changed. The turbulent stress on the forward slope was constant along the slope. It gave a constant flux of frames up the slope, which preserved the slope. It's a self-similar shape,
Yes.
and somehow the turbulent stresses adapt to being a constant stress on that surface.
Yes. Exactly.
All to be explained.
The shape adapts in order to obtain this. What we say exactly. Yes.
The second problem that you had regarding the formation of these liquid flowing on top, The mechanism was not clear. Can you please explain that again? The instability that you got. The previous problem.
The previous, yes, the ripples.
Yes, yes.
The ripples.
Yeah, the mechanism. So, can you think of physical mechanism? What is the physical mechanism? Can you please repeat that? It's not clear to me as to why there is an instability.
The reason of the instability is primarily the phase lag, the phase advance of the shear stress, which drags the particles toward the crests, and then the deposition length, which has the opposite effect, and so that there is a competition between a destabilizing effect, which is the hydrodynamics of the fluid, and a stabilizing effect, which is a deposition effect of the particle. And instability arises when the sum of the two lengths I showed is negative.
You would expect this at higher speeds that this would happen? There's a critical speed above which this would happen?
And no, there is no critical speed. As these waves appear as soon as the particles move. You need only to have some shear stress above the threshold, and then particles, dunes, ripples always go. The shear stress, the maximum of the shear stress, if the maximum of the shear stress is here, you only have wave propagation, as John was saying. And if the maximum of the granular flux is upstream distress, you have there is an instability. Instability needs that the total length, this one plus this one, is negative, so that the maximum of the flux is upstream of the maximum of the bed elevation.
Long live India and France friendship.